So here's how to do some of these extra practice problems. If they involve any types of numbers, I'm going to skip some of them, so we will get back to those ones once we start talking about quantitative force diagrams. So for number one, an egg is free falling from a nest in a tree. We're always going to neglect air resistance unless it specifies us to include it. So our force diagram, start off by drawing a dot. And if it's just in free fall, we're just going to have an arrow going down. Doesn't matter if it's tossed horizontally, thrown up at an angle, thrown down at an angle, tossed straight up. All free fall objects will have the exact same force diagram, just one arrow down. So that's the force of Earth on the egg. So number two, a force is applied to the right to drag a sled across loosely packed snow with a leftward acceleration. So we're dragging the sled to the right, but there's a leftward acceleration. So we got to think that we always accelerate in the direction of the unbalanced force. So let's assume that we've got this person is pulling it and it's going to be on an angle here. So we have our dot, object, we have Earth pulling it straight down. That's the force of Earth on the sled. The person is pulling it to the right. So we'll say it's going to be up and to the right. That's the string here. It's going to be up and to the right. That's the force of the rope on the sled. We also have the ground pushing up on the sled. And we also have friction. Lowercase f, frictional force of the ground on the sled. So this is not an inclined surface or a ramp example, but I do have a force on an angle. So I need to draw in the components for the force that's on an angle. So the force of the rope on the sled has a horizontal component and an upward component. So x, y. So I look at this force diagram and the sled is not coming off the ground, it's not going into the ground, so I need to be balanced vertically. So I have two vectors pointing up, the ground, and this y component. So the two arrows up must equal the one down. So I can't erase that. I'm just going to lengthen this vector. So that needs to equal the y component plus the force of the ground on the sled. So the two up must equal the one down, and it has a leftward acceleration, meaning I need a net force in that direction. So the force of the frictional force needs to be longer than this x component, which it is. So if I can see, there is the amount of x is probably that amount, and then this portion is your net force, your fun ball, your sigma f. So we are dragged to the right, but we have an unbalanced force to the left, giving me my leftward acceleration. Number three, a shopping cart is coasting, not pushed, to the right and is slowing down. So we have our object. Earth is pulling down on the object, force of Earth on the cart. Then you ask yourself, well, what is the cart in contact with? It's in contact with the ground, so the ground is pushing up with the exact same amount of force as Earth pulls down. Because the shopping cart isn't going down into the ground, it's not coming up off the ground. And then it's coasting to the right, meaning it's not pushed, it's not in contact with anything, but it is slowing down. So slowing down, unbalanced force diagram, and what's slowing it down? Friction. So friction is always the opposite direction of the motion. So if it's coasting to the right, friction must be to the left. Lowercase f, frictional force of the ground on the cart. And that's it. Number four. Yep. Number 4, a rightward force is applied to a book in order to move it across a desk at a constant velocity. Consider friction, neglect air resistance. So I see this word constant velocity, and I automatically think balanced forces. So I have my object, always our one non-contact force, which is Earth's pull on the book. It is on a desk, so the desk is pushing up with the exact amount of force as Earth's pulling down. It is being pushed to the right, the force of the push on the book, and it's getting pulled backwards by friction, and friction has to be the exact same length, the exact same amount as the push, because it's moving at a constant velocity and you need a balanced force diagram. So that's the frictional force of the desk on the book. So overall, we have a balanced force diagram, and we are all set for this example. For number 5, a woman exerts 100 newtons of force to lift a laundry basket weighing 75 newtons. So in this case, we have a Earth pulling down, Earth on the basket, and that's the same thing as weight, and that's telling us it's 75 newtons. And then it says the woman is exerting a force up to lift it with 100 newtons, so my vector up has to be longer, so that's the force of the lift on the basket, which is equal to 100 newtons. So 75 down cancels 75 up, and you're left with a net force of 25 newtons. Number 6, 2 people are pushing a disabled car. One exerts a force of 200 newtons east. The other force is 150 newtons east, and friction is 75. So we have 2 vectors to the right, 1 to the left. We have Earth and the ground. So the car is not coming off the ground, so we are balanced vertically. And we have 2 people pushing it to the right, one with 200 newtons and one with 150 newtons. And then friction is pulling it back with 75. So friction is a smaller vector. And that's it. So right now we're not going to include any numbers. And number 7, Mr. Smith and his wife, Mrs. Smith, were trying to move the new chair. Mr. Smith pulls with a force of 30 newtons while Mrs. Smith pushes with a force of 25 newtons in the same direction. Friction is 10. What is the net force? So just drawing the force diagram, Earth pulls down on the chair. The ground pushes up with the exact same amount. And Mr. Smith pushes with 30 newtons, and Mrs. Smith pushes with 25. And friction is 10. And that's that for that one. So number 1 here, it says draw a force diagram for each. When angles are given, identify the angles on the force diagram. So for this one, it's saying that there's a force being pulled to the right. It doesn't say whether it's moving at a constant velocity or at rest or what's going on. Let's just assume that this is at rest. So we have a dot, Earth pulling it down, the ground pushing up with the exact same amount as Earth pulls down. It's being pulled to the right. And if it's at rest or constant velocity, we need balanced forces. So friction must be opposing that pull to the right with the exact same amount of force as that pull. the frictional force of the ground. So we have a balanced force diagram at rest. Now, if it was speeding up to the right, then our friction vector would just be shorter. So a little amount to the left would cancel with that exact same amount to the right, and you would have an unbalanced force. You'd have a net force in the rightward direction, and you would accelerate in that direction. Number 2, you have a 5 kilogram object just hanging from a string, so it appears to be motionless, so we have Earth pulling down on this ball, and the string is pulling up with the exact same amount of force. Here, same object, but now there's 2 strings, so we have 2 forces up. So we have string 1 pulling up and string 2 pulling up. And then we always have our one non-contact force, which is Earth's pull, gravity, and if there's 2 vectors up and if this is at rest, motionless, then the 2 up must equal the 1 down. Oops. So number 3, we have a 7 kilogram object and a 4 kilogram object that's being suspended by a string. So we're just going to draw the force diagram for the 4 kilogram object. So again, it's motionless just like the previous example. We have Earth pulling down on this object. And the only thing that's in contact with this object is just the string above it. And that's it. And now in number 4, it wants you to do the 7 kilogram ball. So just looking at the 7 kilogram ball, we have Earth pulling it down. And also the string that's attached to the 4 kilogram object pulling it down, and it needs to be the exact same length as what we drew here for the Earth on that 4 kilogram ball, because the amount that the string will pull down is the exact amount that the Earth pulls down on the 4 kilogram. So that's the force of the string, bottom string, the ball, and then we've got the 1 string up, and so now we have 2 vectors down and we need 1 vector up, so it needs to be the combination of those 2. So that's the force of the string up on the ball, which is equal to the down string plus the force of Earth on the ball. So I'm going to skip number 5, jump on to number 6. So we have a ramp example. So here we have this object that's sliding down a ramp. So we have an inclined surface. So this is our exception where we are going to draw the components for gravity instead of the vectors that are on an angle. So starting off by drawing, I'm going to start drawing a dot here. We have Earth that pulls down. The ramp's going to push perpendicular, and then it's sliding down. It doesn't say no friction, but it appears that from the little marks here that it's increasing, so it appears that it's speeding up, so we can include a little bit of friction here. But if it's speeding up, we want to make sure we have an unbalanced force diagram. So we're going to draw our components for Earth instead of drawing it for the ramp and for friction. So I'm going to take this vector up and flip it straight down, make it the exact same length. And then I need a 90-degree angle right here, so I'm going to draw my other components down. That's X, Y. So I'm going to need to lengthen Earth's so the arrowhead meets up with that Y component. So if it is speeding up going down, I want this x component